studied bonding and molecular structure. And then toward the end, we did some sort of thermodynamics, which is what connects structure to energy, which is what determines what chemistry will happen. So this semester, we're going to talk about that chemistry, about reaction mechanisms, and about using these reactions to do synthesis. And we'll also do some spectroscopy around the middle of the semester. So just a brief excursion through what we're going to be doing. The first 2 quarters of the semester are going to be on how mechanisms are discovered and understood in terms of structure and energy, what we talked about last time. So first we'll look, naturally enough, at the simplest reactions. There can't be anything much simpler than just cleaving a bond. But remember, there's also the possibility of making a bond at the same time you break a bond. And we introduced these ideas last semester, of course. So we're going to start with free radical substitution, one of the earlier reactions to be studied, as you remember, in the 1830s in France. But we're going to use it to talk about the concepts of reactivity and selectivity. When you can get different products, how do you control or predict which ones you'll get? Then the nice thing about free radicals is they're not charged. So they're relatively insensitive to solvent. So you can just think about the molecules themselves reacting, and whether it's in the gas phase or solution, more or less the same thing. But it's quite different when ions are involved, either as starting materials or products or both, because then solvent effects are very important. So as we go from free radicals, we're then going to do solvent effects, and then go on to nucleophilic substitution reactions, which almost always involve ions, either as starting materials or products or both. And you're going to use that as an example of showing how people go around about proving a mechanism. Okay, then we'll have the first exam on February 2nd. Then we'll go on to electrophilic addition reactions to alkenes and alkynes. You'll recognize that these are concepts we introduced last semester, but this time we're going to focus on how you know about how they work. And we're going to talk there especially about the role of nucleophiles. You usually call these additions electrophilic, but there's quite often a very important nucleophilic component as well. Then we'll get on to polymers and their properties for just a lecture or two. And then conjugation, aromaticity, and pericyclic reactions, which you'll know what they are when we get to them. Then we'll have the second exam. And then we'll have an interlude about spectroscopy and go on to more focus on synthesis. So first, spectroscopy for structure and also for studying dynamics of molecules and reactions. So ultraviolet visible spectroscopy, electronic IR spectroscopy, vibration, which we've talked about a good deal already, magnetic resonance imaging and nuclear magnetic resonance, then on to aromatic substitution, and finally carbonyl chemistry and the concepts of oxidation and reduction. Then we'll have the third hour exam, and the last quarter of the course then will be more having to do with carbonyl chemistry, acid derivatives, substitution taking place at carbonyl group, reactivity adjacent to the carbonyl group, the classical condensation reactions, then something about carbohydrates and Fischer's classical proof of which isomer is which of glucose. And finally, we'll talk about some complex synthesis. We'll be talking about synthetic ideas all through this, but of both unnatural and natural products. Then we'll have the final. So that's how long you have to endure. Okay, so at the end of last semester, we were talking about energy and how it related to things. That free energy determines what can happen at equilibrium. And remember, it was all statistics, and the statistics filtered down to give us this handy relationship at room temperature, that an equilibrium constant is 10 to the minus 3/4 of the difference in free energy, or if you're not worried about entropy, the difference in enthalpy in the heat of the molecules. So that's both energy and entropy, the Gibbs free energy. But there's a completely independent question, which is, will it happen? You know, graphite is more stable than diamond as a form of carbon, but the advertisers tell us that a diamond is forever. Just because it's not as stable doesn't mean it'll convert in any reasonable time. So the questions of kinetics are just as important as the questions of equilibrium, or at least almost as important. And we saw last time that we could approach this by studying lots of trajectories, trying to calculate how all the atoms move and going from one arrangement to another one. But that really provides too much detail. In fact, over the last couple of weeks, we've had interviews from people who are applying for a faculty position here. And a number of them are talking about fancy new ways of actually looking at one molecule at a time as it reacts. All right, so that you actually could do something getting closer to trajectories. But really, that's more detail than we want. We want to summarize things statistically to know what's going to happen in a flask. So we have collective concepts, enthalpy and entropy. And then we can have a reaction coordinate diagram. Remember, we rolled a marble on that thing last time, on that potential energy surface. Or we could slice along the potential energy surface and looked at the starting material, the transition state, and the products. Or we could simplify things to notice that this is just a sequence of three species. The starting material, which is molecules that we know about, the transition state, which we don't know about, and the products, which we know about. So our challenge is going to be to try to figure out something about the transition state, given what we know about the starting material and the products, because its energy relative to those others is going to determine rates. So we have then free energies with just these three species rather than trying to look at a detailed trajectory. Okay, now, so free energy determines what can happen at equilibrium, but also how fast it happens in kinetics. And for that purpose, we need to know that what the energy is, either the free energy or the heat at least, of the transition state. Okay, and remember we talked about this last time, that in the Eyring's transition state theory, the rate constant for the reaction per second is 10 to the 13th times that sort of equilibrium constant between the starting material and the transition state. So again, we can use at room temperature that 3/4 delta G when we express it in kilocalories per mole. So we want to use energies to predict equilibria.